Welcome to the Molecular Structures of Acids and Bases video. By the end of this video, you should understand the relationship between acid strength and bond energy. You should understand the relationship between acid strength and the stability of the resulting conjugate base, and you should be able to make predictions regarding acid strength based on molecular structure. There's a whole bunch of structural factors that determine acid strength. We're going to look at just a few in this video. The main things we're going to look at are the strength of the HX bond, which is highly influenced by the induction effect, and the stability of the conjugate base produced, which is highly influenced by electronegativity and resonance. So let's start by considering the strength of the HX bond. Acid strength, as we know, is determined by how readily an acid will give up its H+. Strong acids give up their H+ easily, weak acids give up their H+ less easily. Therefore, the strength of the bond between the H+ and whatever atom in the molecule it's bonded to is related to the strength of the acid. Consider the two molecules shown here. HCl is a strong acid, which means the bond between the H+ and the Cl- is very weak. It can easily be broken, therefore the H+ can easily be given up. On the other hand, acetic acid is a weak acid, because the bond between the H+ and the O, which connects to the rest of the molecule, is quite strong. Therefore, it does not easily break, and the H+ is not easily given up. Let's look at some evidence to further support this trend. Notice that as bond energy decreases, as the bond gets weaker, the acid actually gets stronger. Recall that lower pKa's are actually stronger than higher pKa's. It turns out electronegativity will play a large role in determining the strength of the HX bond, so let's do a quick refresher on electronegativity. Recall that electronegativity is the ability of an atom to pull electrons towards itself in a molecule. Generally speaking, electronegativity increases as you go up and to the right on the periodic table, with fluorine being the most electronegative element. Looking at three examples of molecules containing fluorine, we see that when fluorine's bonded to itself, because two fluorine atoms will have the same electronegativity, the electrons are equally shared. Therefore, you get no net positive or negative charge in the molecule. You have an even distribution of electrons. However, as the difference in electronegativity between the fluorine and the element it's bonded to increases, we get an increasing difference in electron density, and therefore partial negative ends and partial positive ends, the negative end being around the more electronegative fluorine in each case. So what does this have to do with bond strength? Well, the induction effect tells us that when electrons in a molecule are pulled away from the HX bond, that bond gets weaker. Since we just said electronegativity influences the extent to which the electrons are pulled away from that bond, we can conclude that when a molecule has a highly electronegative element in it, the electrons will be pulled away from the HX bond and therefore make that bond weaker and the acid stronger. Let's look at this example to illustrate the induction effect. Here we see several acids that differ in structure very subtly. Just for clarity's sake, I'm going to go ahead and draw the carbon and hydrogens over here that are kind of understood in this notation. So what's different about each of these structures? Really the thing we want to focus on here are the atoms I'm circling. Notice that as the electronegativity of those atoms increases, the strength of the acid also increases, as indicated by decreasing pKa. Looking at the electrostatic potential maps at the bottom, we see that fluorine is able to really effectively pull electrons towards itself. Therefore, much of the electron density in the molecule will be around that fluorine, giving it a partial negative end and weakening the OH bond. Compare that to bromine over here, which is much less electronegative, meaning it's less able to pull electrons towards itself, making this HO bond stronger. In addition to looking at the electronegativity of the elements in the molecule, there's two other factors that affect induction. First, the number of highly electronegative atoms. Here we see increasing numbers of highly electronegative chlorines as we go from left to right. Because we have more and more highly electronegative elements, we have more and more induction effect at play. More chlorines are better able to pull electrons towards themselves and weaken the OH bond. Therefore, as we increase the number of highly electronegative elements in the molecule, we also increase the strength of the acid. Proximity of the highly electronegative atom also matters. Compare these two molecules. Here, the chlorine is closer to the HX bond than it is in this molecule. Therefore, the induction effect is stronger in this case, where chlorine is able to pull those electrons towards itself and better weaken the HX bond, than it is when the chlorine is further away, making this the stronger acid and this the weaker acid. Here's an example for you to try on your own. There's a lot of information on this slide, so pause the video, consider your answer, and when you come back, I'll reveal it. Welcome back. You should have determined that C is the correct answer. Looking at the diagrams, we see that diagram 2 represents the weakest acid. We know that because it has the most intact HAs and the fewest H3O pluses. Then looking at our electronegativity trend, we see that iodine is the least electronegative of the halogens listed in the choices. Therefore, it will exhibit the least induction effect, causing it to be the weakest acid. Here's another example to try. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. In the first case, we're looking at proximity of the halogen to the HX bond. The closer it is, the stronger the induction effect and the stronger the acid. Here, we're looking at number of halogens. Since we have more halogens on this far right molecule, then we have the strongest induction effect and the weakest HX bond and the strongest acid. That wraps up our discussion of bond strength. Now let's turn to stability of the conjugate. Recall that the stronger the acid or base, the weaker its conjugate will be. In other words, strong acids, like those down this end, will have very weak conjugate bases. Weak acids, like those down this end, will have very strong conjugate bases. It turns out that the more stable a conjugate is, the weaker that conjugate is, and therefore the stronger the acid is. Take, for instance, HCl. When shown reacting with water, we get H3O plus and Cl minus. We know that HCl is a strong acid, meaning that the equilibrium position will lie very, very far to the right. That means that its conjugate base, Cl minus, must be very stable. In other words, it does not have much ability to cause the reverse reaction to occur. The more stable the conjugate is, the stronger the acid will be. So what makes a conjugate stable? Generally speaking, it has to do with the presence of electronegative atoms, the presence of resonance, or some combination of those. Let's consider the presence of a highly electronegative element in the molecule first. Let's start by looking at the structures of some conjugate bases of some common weak acids. The structures of the conjugate bases are shown, and the pKa's of the associated weak acids are shown below the picture. For the conjugate bases, let's focus on these three atoms that are different. Notice that as the electronegativity of the circled atom increases, the strength of the acid also increases, as indicated by decreasing pKa. That's because when the conjugate base of the acid contains a highly electronegative atom, that highly electronegative atom is kind of able to handle or manage the negative charge that the conjugate base will be left with. Therefore, the presence of a more electronegative element will result in a more stable conjugate, therefore a weaker conjugate base and a stronger acid. Resonance is another factor that relates to the stability of the conjugate. At the top here, we have conjugates of two common weak acids. In the first example, we see that the conjugate base exhibits resonance. In other words, that double bond is delocalized and we have some delocalized charge. That stabilizes the conjugate base, making it a weaker conjugate base and a stronger acid. Juxtapose that to the conjugate base shown here, which does not exhibit resonance. In this case, the negative charge has only one place to be. Therefore, it is a less stable conjugate base, meaning it's a stronger conjugate base, which is correlated with a weaker acid. So in summary, the existence of resonance leads to a more stable conjugate base, which leads to a weaker conjugate base, which leads to a stronger acid. Here's one to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Welcome back. You should have determined B as your answer. Since we're asked about strength of an acid, we should be considering the stability of the conjugate base. So we eliminate A and C right off the bat, leaving us with B and D. Lone pairs of electrons are not able to stabilize a conjugate base. However, highly electronegative atoms like oxygen are able to stabilize a conjugate base, leading us to choose B. So let's summarize everything we learned here. First, we saw that the strength of the HX bond determines acidity. The weaker the bond, the more easily the H+ will be given up, the more acidic the substance is. We also saw that elements with a high electronegativity will be able to pull electron density towards itself in the molecule and weaken the HX bond. In other words, highly electronegative atoms in the molecule result in stronger acids. And finally, we looked at the fact that strong acids have a very stable or weaker conjugate base. Conjugate bases are stabilized when they contain highly electronegative atoms and/or when they exhibit resonance. That brings us to the end of this video. Let's review our goals. First, we looked at the relationship between acid strength and bond energy. Then we looked at the relationship between acid strength and the stability of the conjugate. And then we learned to make predictions regarding acid strength based on molecular structure.